I now want to make sure we're clear in terms of what a normal distribution looks like. So first, what is a distribution? The way I like to think about a distribution is just as a list of numbers along with how likely those numbers are. So for example, if you say you're going to flip a coin, what's the distribution of possible values? Well, you could have either heads or tails, and the probability of each of those is 1/2. That is the distribution of the outcome when you flip a coin. If you tell me you're going to roll a die, here are the possible outcomes, and I know that the probability of each of these outcomes is 1/6, right? And I can make a histogram of this one. In fact, I can do it very efficiently because I've already labeled an x-axis here. If you ask me what's the probability that each of these will be the value I see when I roll a die, well, the probability of each of these numbers is the same. They're each equal to 1/6. There's my probability distribution. So a normal curve, a bell curve, is just a probability distribution, but it's for a situation where we have continuous numbers here. In other words, the possibilities are not just 1, 2, 3, 4, 5, but any number in between 1, 2, 3, 4, 5, etc., any real number. The normal distribution, as you've probably seen before, looks like a bell curve, looks like that. And the idea with a normal curve is that you only need 2 pieces of information to convey to someone what your curve looks like. Again, if I tell you that something has a normal distribution, and I tell you its mean, and I tell you its variance, you have everything you need to know. You know exactly what this looks like. A normal curve is centered around mu, its mean. And the spread of the distribution is such that 95% of the values are within 2 standard deviations. I'm rounding, but that's OK. That's conventional. We're not worried about those tiny little digits. 2 is perfect. Okay? So the idea is that if I have mu plus sigma, remember sigma squared is variance, so sigma itself is standard deviation, and I have mu plus 2 sigma. Here I've got mu minus sigma. Here I've got mu minus 2 sigma. The idea is that 95% of the values, 95% of the time, we're in this range. Okay. So if someone says to you, we have a normal distribution with mean 3 and variance 4, then the way to figure out where this normal curve lies is to say, OK, well, I know the middle's at 3. The variance is 4, so the standard deviation must be 2. So if I go up 2 standard deviations, 2 times 2, and down 2 standard deviations, 3 minus 2 times 2, what am I going to get? I'm going to get 7, and I'm going to get -1. 95% of the time, this value is between -1 and 7. Only 5% of the time is this value less than -1 or greater than 7. So that's a normal distribution. Again, the things you need to know about it are that it looks like a bell curve. It is a bell curve. It looks like a bell. It is centered at its mean. 95% of the time, it's within 2 standard deviations of the mean. And all you need to know is that mean and variance in order to completely know what that curve looks like. So one more example of a bell curve. Suppose that I'm trying to figure out what the distribution of women's heights in the US looks like. One hypothesis I might have is that the mean of women's heights is 5'5", so 65 inches. That's one hypothesis I could have. If I want to figure out what the curve might look like, if I assume that it's normal, which is probably about right, what I need to think about is the range of heights that I think are reasonable to see, right? So this is 5'5". I bet, and I'm just making it up, that 95% of women have heights maybe between, I don't know, 5'1" and 5'9". I made that up, but that's not off by too many inches, right? Between 5'1" and 5'9". OK, so I want to set these cutoffs at 61 inches and 69 inches. Based on this guess that 95% of the time women's heights are between 61 and 69 inches, I've guessed the variance. There's an implicit guess of the variance in there. This is mu. I've guessed that the mean is 65, but remember that 95% of the time the values are going to fall within plus or minus 2 standard deviations. 69 is equal to 65 plus 2 times 2. 61 is equal to 65 minus 2 times 2. In other words, I've guessed that 2 is the standard deviation, and therefore that 4 is the variance. Right? So what I have implicitly said here is that the heights of women follow a normal distribution with mean 65 and variance 4. Again, that's a guess, but I don't think it's terribly off. The notation that we like to use for that goes like this. I'll say women's heights follow, the tilde means follow, a normal distribution. Importantly, this is different than the capital N we use for sample size. It's the capital N meaning normal. And what we do is first we write the value we're assuming as the mean, then we write the value we're assuming as the variance. So here I'm saying women's heights follow a normal distribution with mean, mu, and variance sigma squared. In particular, I'm saying they follow a normal distribution with mean 65 and variance 4. From time to time, you'll find people who would rather write this mu sigma rather than mu sigma squared, such that this number is a standard deviation rather than the variance. This is more conventional, but if you're worried about that, make sure you find out which one it is, because there's a big difference between a variance of 4 and a standard deviation of 4.